Hi.
Hi, hello.
Hello. By the way, my name is Yao. What's your name, please?
I'm Hidenori. Nice to
What,
meet
what,
you.
what, what was your name again?
Sorry, I'm Hidenori.
Hidenori.
Yeah, nice to meet you.
Nice to meet you.
Mhm. Yeah. Uh,
I think this is the problem for you.
this is my first time. Yeah.
Oh, okay.
Okay.
Welcome to Pramp.
Uh-huh. Thank you. How about you?
Well, I have been here for a few times actually. I've been here for almost 2 months actually.
Oh, yeah,
Yeah, yeah.
that's good. Mhm.
Yeah, it's a good practice. And yeah,
Right.
let's get started. I think it's your question.
Okay. Right. Well, this is my turn. My okay. The question. Array,
Yeah.
index, and error. Hmm?
Yeah. So the rule is each person has like a 30 minutes to complete, and then
Mhm,
we swap the role, and then we have a 1 hour in total for the section.
mhm. Okay.
Yeah,
Right.
let's get started.
All right. Well, okay, the question, okay, array index and element equality. Um, write a function index equal value search to return the lowest index I for which okay. I see. This is easy question for beginners. I, right. Yeah. I yeah, I separate. uh, I use for and yeah, just for loop. I use for loop. Well, okay. Yeah, this is yes, easy question. Yeah, and um, like result return for uh, uh, array.
Can you? I don't want to
Mm,
interrupt you, but I want you to describe your approach before we dive into the code. I know that you can solve it, and I can see that
uh,
you're very confident. But I want you
mhm,
to walk me through how you have solved this problem. Also I want you to illustrate the time complexity before we dive into the
mhm.
code.
Okay, okay. Sorry. First of all, I'm not good at speaking English. However, I'll explain. Well, yeah. In this question, I'll solve to use just for for loop, and the time complex is obviously order the n, which is the length of array. Well, the first, well, scanning each element, and well, the index will be started from well 0 to n minus I, and then if I find uh, the index which is matched uh, uh, elements value and the current index, and then I return. that are in current index. If not, I'll return well, minus 1. Does it make sense?
Yes, that's a very good starting point, but that's too easy.
Mm.
And also the time complexity for your approach will be O of n, right?
Yeah.
And this is a very good starting point, but I want you to optimize this approach. I know that this
Mm-hmm.
could be a solution like scanning each one of them, and then
Yes.
when we find the one
Mm-hmm.
that is the value is equal to the index we return, right?
Yes, that's right.
Yeah. So that's a brute force approach, but I want you
Yes.
to optimize this solution definitely can work, but I want you to optimize the approach. We have so that we can have a faster algorithm.
Mm-hmm.
So yeah, think about it. How can you optimize the approach that so that you don't necessarily have to scan each one of them.
Well, I see. Okay. So
Yeah, that's why I'm going to give you a little bit of a challenge. I know that we can do I know that we are very confident on the approach. I know that it's gonna work, but I want you to optimize it.
Okay, I see. Well, okay, right. Mm, Optimize. Yeah. Yeah. Okay. Okay. For example, okay, if we need to search uh, many times, in that case, using hash is better. Or for example, first, uh, well, mm, for example, I think we need to uh, scan each element once.
Okay.
It's necessary.
Well, I think you can do better than that. You don't have to scan every single one of them. That's why you can be faster. Also, I don't think you
Mm.
need you don't need a hash map.
Uh-huh.
Yeah,
Mhm.
I leave it to you because we still have some time. We are only like 8 minutes in. I want to give you some space to think about it. You don't necessarily have to scan each one of them. Also,
Mhm.
you don't need a hash map. I don't think you need a hash map. I give you
Oh,
a
I
challenge.
see. Uh,
Also, I'm gonna give you
mhm.
another hint. I'm gonna give you a hint.
Mhm. Mhm.
So I'm gonna type it in the screen so you can see my
Okay.
hint. Okay.
Okay. Thank you.
Um, yeah, in a real interview, you always can ask for hint in the. So this array is sorted. You see that?
Yes.
Sorted. Yeah. So
Mhm.
it is sorted. You can use this information to your
Mhm.
advantage.
Mhm.
Is in your approach, you can do it like for unsorted array, you have to scan every single one of them. But in this array, it's sorted though. It's in some order. You can use
Mhm.
that information for your solution.
Uh, okay. Yeah. Yeah. I missed sorted array. This is sorted array. Okay. Well, yeah. And in that case, well, I can use binary search also. Well, binary search.
Yes, exactly. Use binary search.
Yes, binary. Yeah. So uh, using binary search reduce time complexity from order n to order log n. Yes, order binary search. Binary search. I binary search. Okay. Or binary search. Binary search. Okay. Binary search. Cool. Just a moment. I'm thinking now.
No problem.
Okay. Binary search. Yeah. Now I'm thinking about how which direction I need to move. Well, well, I'll type. Well, this is a typical binary search form. The left and right, and array, and then while middle index is plus, and then well array m equal or blah blah. Sorry, and go r go and minus. So this is typical binary search form. However, well, I'm thinking about this judgment now.
Well, that's a very good starting point. I think. Yeah. So this is blah blah blah, right? This
Yeah.
XXX, and in translate to this problem, it's gonna be we are looking at the value, which is here,
Yeah.
right? This is the value, and compare that with some sort of, in this case, it's an index.
Yeah.
So if that value is equal to something, I think should be maybe index.
Yeah, that's right. That's right. That's right.
Yeah.
This is index. Yeah, index equal return obviously return. And however, if if they are different, well, different.
Yeah. So this is one of the cases. If it can be equal, can be others. Like, I leave it to you. I don't want to give you away.
Okay. Wow. Right. A fixed type. Oh. Ah, oh, oh, okay, okay, okay. Well, oh, yeah. In this case, yeah. Just comparing the value of array, current index value versus m index in current index. Yeah. So if array m larger than current index, well, current index L equal m plus 1. Yeah. Okay. Yeah. This is my my answer.
No, let me see. Not quite. I want you to think about these two conditions, these two execution again. So when the value is greater than the index, right?
Yeah. Yeah.
So that means if we still, so this one is means that L, this means we are going to the right. This means going to the right partition.
Well,
Think about this again to see that that's exactly what you need. Because the current value is greater than the index, and if we go right,
yeah,
the index will increasing, the value will also be increasing, but the value is already greater than the index. You think about this.
Yeah, yeah. I see. I see. Okay.
So both of them will increase by at least one, right? The index will increase by at least one, by one, but the value will be increased by at least one. So if we still go right, we are not necessarily going to the right direction.
I see. I see. All right. Yeah. Like this it.
Yes. Yes. This is much better. However, yeah, this question looks easy. I thought it was easy at the beginning as well, but it's harder than I thought actually when I solved it. Also, there is another constraint. We have to return. So as you can see, we need to return return the lowest.
Lowest.
So that, yeah, the lowest index. That means, let's say if we are given an array 0, 1, 2, 3, and then all the way to 5, 6, 9, 11, something like this. This, your function, your entire function, need to return the index at the lowest level, which is the 0. Even though this one is matching, this one is matching, this one is also matching, but we have to return the lowest number, which is at the beginning. But in your algorithm, you will return it at the middle. So that's why you have to implement a small tweak, a small change, improvement, to make sure that you return the lowest index.
Okay. Lowest index.
Yeah, that's what the question is asking. Lowest.
Oh, I see. I see. Yeah. Shouldn't return here.
Yeah.
Yeah.
yeah, this one exactly. You can work on this statement when it's found when it's found the first one, which in this case will be the middle first, right? And then it's done. It's not yet done. We have to still go through the other stuff to make sure this is the lowest.
Okay. Oh, all right. Yes. Wow. Okay. Cool. Yeah. Result. Right. Right. Yeah. This is my answer.
Okay.
Okay. And then can I write this code? Sorry, down this code or part.
Yeah, you can run it, but this is not quite correct.
I see.
Yeah, it's not quite correct because basically you return in the M. Let me think. Maybe we can run it to see if that works, and you can see. You can run the test to see if you want to see. The button, the green button at the bottom. Run test. Yeah, you can run the test to see if that works.
Yeah, but this is not correct answer.
Oh
no?
Well, it's close to correct. Because. So can you walk me through your algorithm too? I mean, what do a dry run of the example like this, and then to see how it works.
Right. Well, first L equal 0, R equal equal 6. 1, 2, 3, 4, 5, 6, 7. Okay, and then middle equal 3 equal 1, 2. Okay, hit and result equal 3. Then right equal 2. The next is 1, L equal 0, R equal 2, and then 1 equal 1. 1 equal 1 equal 1. And then 0. And then yeah, that's true. Equal, yeah.
Yes, exactly.
Yeah, exactly.
There you go.
So this is correct answer.
Yeah, I think now looks okay. I think it's really good. That you can run the test to see if that can run too. Press the green button at the bottom.
All right. Run test. Oh, okay. Yeah. Thank you so much.
Yes. So that's the little twitch that you miss is for binary search is always smaller than greater than equal to. I missed it when I wrote it. First time when I solved the problem, I missed that condition, and the interviewer corrected me. So yeah. So this is the approach, and this one is always can find the lowest index, which is 0 in this case.
Okay.
Okay, I think you solved it within the time limit, so it's really good. You have done a good job.
Thank you so much.
And okay, now let's swap the role and then become my turn.
Okay, suppose.
Okay, so let me see. Largest, smaller binary search tree. Okay. Wow, what's this? So it's law of code already. Let me see. Given the root of the numbers multiplication function defines the largest key in the tree that's smaller than num. Okay, if such it doesn't. Okay. Keywords are largest key in the tree that's smaller than num. Okay. Okay.
Okay.
Okay. Wow, this is it's not easy. I think the first thing, the first thing that I come into my mind will be the binary search tree, right? So for my understanding, and everything on the left will be smaller than the root, and everything on the right will be bigger than the root. That's what we mean by binary search.
Yeah, true. Yeah, right.
So, let me see. I already have a chunk of code given in here. So the method, okay, lines 30. Oh, okay. So that's the function. Okay. Understand. I'm looking at reading this instruction. So use the helper function code to implement. In a nutshell, the helper code allows you to build a binary search tree. Jump to line 71 to see an example to see how helper function. Okay.
Yeah. You're right. This function.
Yeah. Okay. I understand now. Okay. Let me think. So basically I need to find the number, the smallest number, the biggest number. The biggest number. Let me see. The biggest number that's smaller than the target. I think this is our goal. So largest number in the tree that's smaller than the norm. Okay. I think. Okay, so this is my thing. My thinking. Okay, so.
Okay.
The target. I'm gonna write some my idea first.
Okay.
And then you can correct me if I'm not in the right direction before I jump into code.
Okay.
So now we have the target, right? So we are given a target. The target is given, and if the current number that that is less than, or is less than, is less than the target. And what we can do is to, because that means the number is too small, we want to make it bigger. That's why we can go to right. Right? And if, hang on. If, it's too small, we can go to the right. The right child of the current number. The right child of the current number. Call it current num. If the current num is too small, we go to the right child of the current num. So basically we call, you understand what I'm saying, so I don't need to say more.
Oh, yeah. Okay.
Yeah. So if that is too big, it's bigger than the target, we go to the left child of the current num. And also we're looking for the number that's smaller than the current num. Actually, we found that one potential candidate already in here. Right? So that means, to me, we have some sort of we have to compare all the possible numbers. Right? If let's say if the target is, in this case, is 17, if we found something like a 16, we are done. Right? So if we found something like a 16, because this is an integer, right, we are done. But if we don't find 16, we have to keep traversing, going through all the nodes. So that means, binary search tree. I don't want to traverse all the nodes though, and that's why we can use the binary search nature of the tree, which I can use the big O of a log n, like a binary search, basically, sort of like a binary search. I think, so in here, if the current number is smaller than, so we also want to have a largest key. So we have the result, right? So the current result will be equal to the current num, will be the maximum of the current num and the result. So at the end, we will return the result, right? And then at the end, we will return the result because we want the largest number. Do you agree?
Yes. Correct. Yeah. Great. Yeah. I think. All right. Yeah. All right.
You think
I totally.
You think this is the correct approach?
Yes, exactly. Yeah.
Okay, and for the time complexity, it will be big O of log n.
Yes.
Because we don't necessarily traversing all the possible nodes.
Yeah. True. Yeah.
Okay.
Correct.
And
okay.
Okay. Thank you for confirming. Let me think. Still.
Okay. Yeah. Your approach method is quite good. Good. Yeah.
Okay. Understand. Okay. Thank you. Let me think. So. Okay. So result equal to binary. I'm going to scroll to the bottom. So result equal to binary search tree to find the largest number. Okay. Okay, let me see the structure.
Yeah, that value is root by a
Yeah,
service root. Yeah.
yeah, I'm thinking, okay,
Mm,
I'm thinking, how can I, okay, self.root is,
mm,
I'm thinking, how can I traverse? Okay, okay, I understand now.
okay.
So, yeah, I think it should be okay. Okay. So what I'm going to do is the following. So I'm going to use a depth first search. So a stack. I need a stack. Right? So a stack is
Mm-hmm.
equal to self dot. Um,
Stuck.
yeah, I stack. So um, I'm thinking how. So
Mm.
the given uh, yeah the given this is the class, right? So where is the root node? In this case, where is the 20, right?
Yeah. This is the root of a BST, and then
So this
yeah,
so self dot root is the 20.
20. Hmm? Sorry. What is 20?
Yeah, 20 in this example is the root node, right?
Oh. Mm.
In this example, like 20 on the left is 9, on the right is 25, right?
Oh yeah. It's yeah.
So self dot root
Right.
is equal to the node that has a value of 20.
Yes. 20. Yes.
Okay,
That's right. Yeah.
okay, understand. Okay. Uh, okay. So maybe I can do a recursion. Uh,
Mm-hmm.
recursor. Recursor. Okay, so I will need a node, and so also I need a result, right? So result equals to well, I can start with negative infinity,
Mm-hmm.
right? And then if node dot node dot key, in this case the key is less is well, if node dot key is less than, or yeah, less than the number, and
Mm-hmm.
what we're going to do is the result equals the maximum of the result and node dot key, right? And also
Mm-hmm.
yeah, and also I will go to the right child of the current number, right? So and that means I need to call the recursor, the function itself,
Mm-hmm.
on
Yeah.
the right child. So that means it's the node dot right,
Mm-hmm.
and yeah, so and then that's it. So don't need to do the rest. I'm going to return. So so if
Mm-hmm.
um is greater than the number, that means I need to search for the left. I need to make the number smaller. So go to the left. Right. Also, I'm going to return it. And if it's exactly that is equal to the number, so what do I do in here? If the number key is exactly equal to the number, in that case, I still go to the, it's still too big. I still go to the left. Yeah, right? Do you agree?
Sorry, once again, please.
Yeah, when the node number is exactly equal to the target, we are still too big, right? We want to go smaller. So in that case, I put it here, small, greater than or equal to.
Equal to, yeah.
Right. Yeah, and I think at the end, yeah, and to trigger the definition running, so I'm gonna trigger self.root, right?
Yes.
This the top of all the nodes, and then at the end, I'm gonna return the result. Do you agree?
Yeah, basically, yeah, your code is correct. However, if I not found, well, yeah, if it doesn't exist number, that number, we need to return -1.
-1.
Yeah. This is yeah.
Okay. I understand.
So
okay,
yeah,
good.
but it's minor.
Yeah. No. It's very key. So if the result is equal to thank you for noticing that. Return -1. Else return the result.
Yeah. I think this code is okay. Result.
Local variable.
Scope.
Okay.
Scope.
Scope.
Yeah. This is
Let me think. So it's here. Yeah. Okay. Trace back. Result. Reference before assignment. Okay.
Local value.
Why is that? So in the recursor, unbounded local error. So local variable result is reference before assignment. Okay, so that means the result. Okay, so it's saying I understand what you mean now. So maybe I need to pass in the result, and also pass in the result in here, so I can pass through the variable.
Yeah.
Yeah. Oh, come on.
Yeah. Keys.
Non-type as an object or key. Oh, I think. Oh, okay. I understand what it means now. So, yeah. So what it's saying is, yeah, if in a case where there's no left and no right, and yeah, in the case where, let's say, if we are at like a 5, 11, 14, and 25, they don't have a left or right,
mm,
right?
yeah, sorry. Yeah, sorry, yeah, okay.
So, okay, so that means, but we can call back the parents though. Okay, so
Sorry, I missed not get the point. Yeah, sorry.
yeah, that's okay. I was thinking how to approach this now. So because if there's, let's say, if there's nothing on the left and there's nothing on the right, we cannot do that.
Yeah.
That's why it's just on the leaf node. On the leaf nodes, we cannot do that. Yeah, so I'm thinking, if we are at the leaf nodes. Okay, so here's what I'm going to do. If node dot left equals to none, yeah, in that case we don't need to do anything. And yeah, right, so basically we don't need to compare anymore.
Yeah,
However,
but
go ahead.
Oh, sorry. But in this case, well, node has its value, right? You don't need to compare with the target number.
Oh yes, you're right. I still need to compare the target number. You're right. So if node dot key is smaller than the num, still, so the result let me think. So okay, let me think about this. So
okay.
I understand what you mean. So the maximum of what comes back and the key. Okay, I should do this. Let me think. So what comes back is okay. Yeah, in this case, we return the key value. And I don't need the result anymore, I think. If that's greater. Is it correct? Oh, let me think. So if there is no child, right, left is equal to none, right is equal to none, and then if the value is smaller than the number, we just return the key.
Oh,
Right.
if not, yeah,
Yeah, if
else,
not.
else case, else case is
Yeah,
return.
else. Yeah, and then else if equal to if.
Oh, okay. Else, fine. Sorry. But in this if state, yeah, well, in this if sentence return dot key, right? And then, however, well, sorry, else, do we need to return anything?
Oh, okay. Yeah. If that's okay, I see what you're saying. So else just return um
Yeah, yeah. Okay, sorry.
let me think. Return something. Let me
Okay.
yeah, it should be
Uh,
return something.
I
Return.
think, yeah, I think the first approach is easier. I think first approach is not use return values.
The first approach
Uh,
is easier. Oh, you mean
yeah,
put in the result?
well, how can I say it? Well, y- well, first you use argument, right? Result,
Yeah.
and not use return. However, now you use return some values without uh, using argument, right? But however, I think in this case, using result, which is the first approach, is easier. I think.
Okay. Okay. Understand.
But
Okay.
you need to change the code.
Yeah. It doesn't. Okay. It's okay. So okay. Okay. Understand. So in that
Mhm.
case, result equal to maximum of the result. Oops.
And then, yeah, and then sorry, can I give you advice?
What was that?
Sorry, can I give you some an advice? Advice?
Yeah.
Yeah,
Please.
yeah, yeah. Well, this sentence, how we can write more simply. Well, for example, uh, not not uh, equal return like that. It's easier in this case. Well,
Oh.
which
Okay.
means,
Okay.
uh, yeah,
Okay.
this is difficult. Yeah,
Oh. Okay. Okay. Good.
right.
Okay.
Mm.
Yeah. Thank you. So yeah, if not node. Yeah, not node return, right? And so I don't need this chunk of code anymore.
Yeah.
Thank you. So let's go back to, so if the key is less than that, and what we're going to do is the result.
Sorry.
Okay.
Sorry.
Yeah, that's okay. Maximum.
Okay.
The key value and the result. And at the same time, I'm going to recursively call the right side. Yeah, that's right. So the right. Yeah. Yeah, so like this level like this. So if that number is bigger, yeah. So yes, so like this.
Yes. Yeah. Okay.
Let's run it.
If not,
oh, okay, here.
indent. Yeah. This is.
Okay, so the indentation. So I put it here,
Okay.
maybe.
Sorry. Yeah. One. Sorry.
Largest number is -1. Oh.
Okay.
So
One.
let's see.
Yeah. Okay. Sorry. Well, sorry. I think. Well.
Yeah, the result is not being returned. Okay.
Yeah. Well. I don't know. Well. Sorry. I don't know. Well, about Python's grammar. Very well. However, I think I need to change this coding style. For example, the simple way is felt result equal mass float and then we use like that. I think this is a very easy way to solve this problem.
Okay.
Yeah, I think. Sorry.
Okay, yeah, we don't need this one anymore.
Yeah.
Let me think. So okay.
Yeah, like this. I think. Yeah. This is good. Probably. Oh, sorry. int.
Int object is not objectable.
What? Oh, sorry. I missed that. Result. Yeah.
Oh yes.
Sorry.
No, it's okay. I think it looks good now.
Yeah.
Ah, yes.
Yeah. 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 So
Thank you.
yeah. 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 Good. Yeah.
Okay, thank you so much. And by the way, I'm
Mm.
where you are right now. You are in. I think you're in Japan.
Yeah, that's right. Yeah, I live in Japan. How about you?
I'm in Canada actually.
Canada. Oh, right. Oh,
Yeah. So
okay.
are you actively interviewing companies?
Actively in what? Sorry. In
Are you looking for jobs and interviewing companies?
no. Yeah, actually, yeah, I'm working for an IT company now. However, yeah, I'm I'm well, I'm going to thinking uh we're thinking to or take an interview for some IT companies. Yeah, in the future,
Yeah.
within
Oh, okay.
this year.
Yeah, I interviewed with Google.
Mm.
Uh,
Oh,
yeah, but I didn't make it, so I wasn't good enough, and that's
mm-hmm.
why I came back to Pram to get practice.
Oh, I see. Google. Yeah, this year you challenged.
Yeah, yeah.
No.
This year, yes, it's this
Oh,
year.
yeah, yeah. Yeah. Me too. I'm going to challenge Google. Uh, it at the end of this year, probably. Yeah, but it's Japan, probably. Mm-hmm.
Which company are you working for right now in Japan?
Well, yeah, maybe IT companies like Google, Apple, Facebook, like that. How about you?
I
Hmm,
yeah, I'm working. I'm working for a bank right now, a bank in Canada.
Bank,
Yeah,
bank? Oh, really? Hmm.
yeah.
Are you are? Mm, sorry. Go ahead.
Yeah, and also in computer programming for a bank and
Mm,
Scotia Bank. I
mm,
don't know if you know Scotia Bank. So
mm,
yeah, I really want to work for a bigger company like Google and Apple, like what you said.
mm.
Yeah,
Yeah, yeah. Great, great.
yeah.
Mhm.
I'm gonna leave my LinkedIn in here just so in the future if you come to Canada you can ping me, we can connect.
Oh, okay. Oh, thank you. Hmm.
Yeah. So I want to connect with you on LinkedIn. If you go to the top, you can see my LinkedIn. That's me.
Top. Top. Oh, okay. I see. Yeah. I
Yeah.
will. I will check it later after this. Right.
Yeah.
Thank you.
Okay. Yeah. Thank you so much for your
Mm,
time. I really appreciate it.
mm. Me too. I'm appreciated. Yeah. Thank
Okay.
you.
Good luck to your job search.
Mhm.